Okay, so hello everyone, good day. I'm very happy to be here and to have the opportunity to present this talk to you. So the idea behind this presentation is actually to show you a module for the derivation of gravitational waves that I have implemented in Phantom thanks to the help and to the guidance of Daniel Price and David Liptai. So I will show you the details of this tool and also how we use it to study gravitational wave emission from a particular type of astrophysical system that are tidal disruption events. And at the end, I will also illustrate some possible other way to use this tool and possible way also to improve it. So let me start actually with an overview about gravitational wave astronomy because, well, I'm not sure how much familiar you are with this topic, and also because I think it's kind of fascinating starting from the beginning. So in 2015, and actually the announcement was the year later, there was the first direct detection of gravitational waves. So for the first time, actually, we saw a stellar binary black hole merger. This was for sure an outstanding event in astrophysics because it was the first direct detection of gravitational waves and a further confirmation of the theory of Albert Einstein. And we can say that since then, the gravitational wave astronomy field kind of exploded because since 2015, we have already detected around 90 gravitational wave events. The majority of these are binary black hole mergers, but we also have neutron star mergers, for instance. So how do we detect these events? Well, what we use are ground-based interferometers. And I think actually that these instruments are among, if not the most sensitive instruments on Earth, because they need to be able to actually measure differences in length that are 1,000 times smaller than the size of an atom. In particular, to present day, we have a network of three active detectors. We have LIGO, that is actually made of a couple of twin detectors, and it is based in the US. We have VIRGO, based in Italy, and recently also KAGRA, the underground Japanese detector, joined the collaboration. But what's happening? Okay. We have also many other things in the future. First of all, in 2037, the first space-based interferometer will be launched. This is the LISA mission, the Large Interferometer Space Antenna, that is a project mainly funded by the ESA, the European Space Agency. And thanks to LISA, for the first time, we will be able to see the gravitational wave sky in the low frequency regime, in particular in the range between the milliards 10 to minus 4 hertz actually, and the Deci-Hertz. And it is a particular interesting range because here we can see supermassive black hole mergers. But then there are also many other suggestions for the future after LISA. In particular, the most promising suggestion at the war is what they are called Deci-Hertz observatories. That is interferometers that, with respect to LISA, are orders of magnitudes more sensitive in the Deci-Hertz band. It is a particular interesting band because it's where we can see intermediate mass black holes. So this elusive population of black holes that we hope they exist, but we're still not very sure about it. So given all these premises, let me also say something, not too many details, about general relativity. Because when we talk about gravitational waves, actually we need to go back to Einstein field equation. So basically GR is telling us that gravity is a geometric features. So we can think of it as the curvature of space-time that is curved because of the presence of mass and energy density. In particular, general relativity predicts that accelerated asymmetric mass distribution perturb the space-time. And this perturbation is what we call gravitational waves. And a gravitational wave passing through the universe affects the distance between two objects. In particular, we call gravitational wave strains, normally indicated as h, the ratio between the difference in the length due to the passage of the gravitational wave and the original length. As light, also gravitational waves are polarized. And actually in GR, we expect two polarization, the plus polarization and the cross polarization, that can be thought as a different pattern of oscillation of a ring of test masses when gravitational wave passes through them. So, okay, now you know everything about gravitational waves. And the question is why we should implement a gravitational wave tool in Phantom. Why Phantom is the right code to do this? Well, first of all, because we all love Phantom here and we want to use Phantom for everything, for sure. But then actually there are two features in Phantom that are very interesting for gravitational wave studies. First of all, since Phantom is an SPH code, it's particularly well suited to simulate non-axis symmetric systems that are the interesting systems when we want to study gravitational wave emission. Moreover, since 2010, we also have GR Phantom. That is, with Phantom, we have general relativity implemented. It is possible to simulate astrophysical system in a fixed background metric like Kerr metric. So these features make Phantom a perfect code to simulate this tool. And also Albert Einstein is happy with the choice. So we can proceed. Okay, so what we did, let me start saying that actually a first tentative of using Phantom to calculate gravitational wave emission was already done in 2019 by me, Rebecca Nilon, and Giuseppe Lodato. In this case, we were interested in studying an unstable accretion disk that could potentially form after a tidal disruption events. But in this case, what we did was do the simulation and then after in post-processing, write a routine to calculate the gravitational wave emission. But then during my first stay in Australia, talking with Daniel and David, there was another idea. So create a module that on the fly, so while the simulation is actually running, is calculating gravitational waves. Well, what we did in practice to write this module was transcript numerically the quadruple formula, the quadruple approximation, that I know is an approximation for sure, but I think it's already a good starting point to begin studying gravitational waves. So this approximation is telling us that the gravitational wave strain is proportional to the second time derivative of the moment of inertia of the system. So basically what we need to write in Phantom is the second time derivative that can be expressed in terms of typical quantities that describe SPH particles: mass, position, velocity, and acceleration. The idea is that this quantity is calculated while the simulation is running, and then it is used, is plugged in the expression that we use to formulate the two polarization amplitude H plus and H cross. But in order to do this, we also need to define three angles. One angle is actually the rotation of the XY plane. Another angle is telling us how we look the system. So basically it's the angle between the line of sight and the normal to the orbit. And the third angle is instead is the projection between the line of sight on the XY plane and the Y axis. I understand that right now these angles can sound a bit abstract, but then when we talk about a particular physical system, they become more clear. So we implemented actually this model in Phantom, and we also do some tests to verify that everything was working great. And actually, yeah, we were very happy because everything was working great. So once we had this, we decided to applied to the case of tidal disruption events. So let me explain a little bit what are these sources. Tidal disruption events occur when a star orbiting around a massive black hole is disrupted due to the black hole tides that overwhelm the stellar self-gravity. We can have full disruption or partial disruption. Here in this talk, I will just focus on full disruptions. And when the star is disrupted, we expect roughly half of the stellar debris to circularize around the black hole and eventually, maybe, form an accretion disk. We're still not very sure about this, actually. So, why tidal disruption events are interesting? Well, because they are multi-messenger emitters. As a matter of fact, they emit electromagnetic radiation. And we know this for sure because it's the only way so far we have really detected tidal disruption events. In particular, this electromagnetic radiation is produced during the circularization phase, where the stellar debris starts to accrete onto the black hole. And to date, we have around 100 observations of tidal disruption events, mainly in optical and X-rays. Then they also emit high-energy neutrinos that are produced from the later stages of the events, when there is also potentially the production of jets. To date, we have just a few potential candidates of astrophysical neutrinos from tidal disruption events. And eventually, they produce gravitational waves. That is actually what is more interesting to me. And please keep in mind that gravitational waves is basically the only way that we have to detect these events during the moment of disruption itself. Because as I told you, electromagnetic radiation is produced at later stages, while gravitational waves is already produced during a disruption. So let me say something more about this gravitational signal. So the gravitational signal is due to the time variation of the black hole star system mass quadrupole. And we can approximate it, just to do some analytical estimates, as a monochromatic burst. In particular, if we assume the standard TDE scenario, that is a sun-like star disrupted by a 10 to 6 solar mass black hole, that we assume at a typical distance of 20 megaparsec, we have that the strain is around 10 to minus 22, with a frequency around 10 to minus 4 hertz. Instead, if we consider a white dwarf, tidally disrupted by an intermediate mass black hole, well, in this case, the strain is of the same order of magnitude, but the frequency is higher, it's around the Deci-Hertz. So as you can see from this plot, I put the two little stars, one representing the estimates for the sun-like star, and the other one represents the estimate for the white dwarf. So as you can see from this plot, actually, these sources are potential interesting targets for future space-based detectors, because this signal actually will increase along the green arrows if we consider the star closer to the black hole. Okay, so in the future, for sure, actually, we will see tidal disruption events with gravitational waves. From another work that I did that I'm not presenting here, we expect that with Deci-Hertz observatories, we can actually observe thousands of tidal disruption events per year. So we need to know in advance how the signal that we will observe look like. We need to be ready. This is why we decided to apply phantom to the case of tidal disruption events. And this is what we got. So here is the signal from a standard TDE, so from the sun-like star disrupted by a 10 to 6 solar mass black hole. You can see that I plot the two polarization amplitudes and also the associated burst. In this case, I assume that we are observing the system face on, and we are locating, like always, the distance at 20 megaparsec, the system at 20 megaparsec. So actually, when we got these results, we were quite happy, because the signal we got was in good agreement with the analytical estimates, both for the peak of the amplitude, but also for the duration of the signal. So after this promising result, we decided to use the tool to start exploring the parameter space of tidal disruption events. And so in particular, understanding how different values of the parameters that describe TDs can actually affect the gravitational wave signal. Okay, so for instance, here you can see gravitational wave signal produced by tidal disruption events where the black hole is spinning. We have different values of the black hole spin, A, and we are considering one case prograde orbit, in the other case retrograde orbits. And what we found was that actually the gravitational wave signal increases here for lower values of the spin in the case of prograde orbits, while the opposite trend is observed in case of retrograde orbits. And this is something that makes sense because it can be explained with the orbital frequency of a test particle around a Kerr black hole. Another result that we got here is how different inclination angle of the stellar orbit can actually affect the gravitational wave signal. So here there are 4 plots. On the top line actually, we are considering a static black hole, so A equals 0. Here we are considering, in the bottom line, we are considering a spinning black hole, A equals 0.9. And if we consider the left column, beta is equal 1, where beta is a dimensionless parameter called penetration factor that quantify how close the star is to the black hole. So beta equal 1 means that the pericenter of the star is equal to the tidal radius, that is the maximum distance from the black hole to have a TDE. Beta higher than 1 means that the star is going closer to the black hole. In the right column, beta is equal 5. So what we got? Well, when the black hole is not rotating, actually, as you can see, different inclination angle does not affect the gravitational signal in any way, which is another reassuring result because we were expecting this. As a matter of fact, there is spherical symmetry. Things are different in case of rotating black hole because here, where beta is equal 1, so the star is quite far away and the spin effects are negligible, we still are in the same, the spherical symmetry still holds. But here, when the star is closer to the black hole and so the spin becomes important, you can see that for different inclination angle, we see a difference also in the signal. Another result was also try to understand how the signal was affected by the eccentricity of the star, of the stellar orbit. And also in this case, you can see that actually the signal increases for higher eccentricity, which is also something that can be explained from a theoretical point of view. So all the results actually we got were consistent with what we were expecting from theory. And finally, let me show also this signal where we are considering a stars disrupted by a black hole and then the debris start to circularize back, so start to return to the pericenter. So here you see there is the first burst, that is the one associated to the disruption phase, and there you see another small peak. It is the first passage at the pericenter of the stellar debris. So for sure, as you can see, I mean, the signal is more than 1 order of magnitude lower than the main contribution due to the disruption. But yet in the future, we could have at some point also interferometers sensitive enough to see this peak. And when this will be possible, for the first time, we'll be able to see the circularization process both through electromagnetic radiation, that is something we already do, but also the gravitational waves that will provide the complementary information. Sorry, let me drink a little bit. Okay. So, what can we do next? First of all the results that we got thanks to this phantom tool for the gravitational wave emission are collected online on that website. So for now, there are only 200, a bit more simulation, but actually the idea is to make this catalog bigger. And why this? Well, because we like simulating stuff with phantom, for sure, but also because if the number of gravitational waveforms for tidal disruption events actually increase, they can be used to fit a possible gravitational wave signal observed from possible tidal disruption events. And this will be something very important to do, because if we are able to detect electromagnetic signal, gravitational waves from tidal disruption events, TDEs can actually become a way to constrain the present value of the Hubble constant that we know is kind of a problem, because there is like the famous Hubble tension problem where we have different results from CMB and gravitational waves, and we don't know how this can match, how the two results can match. But also, other things that we can do is actually explore other systems or variation of tidal disruption events. Like, for instance, one thing I would like to do in the following months is study the gravitational wave signal from a partial tidal disruption events. Because in this case, since actually the star is continued to, what remains of the star is continued to orbit around the black hole, the signal to noise ratio can actually increase a lot, and this can become promising for future detection. But also, for instance, what is the gravitational wave signal of a TD around a binary black hole, or a TD of a binary star around the black hole, where there are infinite possibilities to explore. And also another thing that, for instance, was in my mind, it was the gravitational wave signal associated to planet disruption, that I think is quite weak, but maybe for background studies can be interested. And then another possibility, I'm not really sure, but why not, is actually introduce post-Newtonian formalism in this tool, which would be great because it will become more precise. And with this, I finish my presentation, and I thank you for your attention.
Do we have any questions? Yep. Okay, let's just start here.
Hi, thanks for the great talk. I was curious, you talked about the Hubble constant measurement. That was in terms of a bright siren, right? What happens if you don't have an EM counterpart? Is it still useful?
It will be for sure more complicated.
Okay.
But I mean, disruption events are very luminous, actually. We expect that in the next year, with instruments like Vera Rubin Observatory, we will see thousands of TDs in electromagnetic radiation. And I mean, the main problem in this case is the rush, because they're very far away, and observation can be more complicated. So yes, what actually was in my mind was a combination of electromagnetic information and gravitational.
Yep. And yeah.
Thank you for the nice talk. You mentioned that you also consider both like solar mass stars and white dwarfs, right? I was wondering what will happen if you have like either evolved or massive stars that are being disrupted, because if either evolved giants or more massive stars, because for example,
there are actually already some studies about this. If you consider like a red giant, for instance, around a black hole.
Either this or maybe a massive star.
The fact is that in that case, it's more likely that we have probably a partial disruption, so like the external layer of the contain, and there is like a compact particles with this parts.
Okay, thank you.
Do you calculate with full general relativity? I saw you had a post-Newtonian approximation that you were going to deal with later, but basically it's a perturbation calculation that you use to get the wave? Right.
I think actually it can be interesting, since actually phantom is not a proper numerical activity code. This can actually be very interesting to have post-Newtonian formalism implemented in the calculation of gravitational waves, because it increases the accuracy.
So what's the main error in your calculation? The perturbation estimates, or?
I mean, this is just an approximation that holds in case of weak field. But in case of tidal disruption events, if we are quite far away from the black hole, this should be fine.
The other question I was going to ask is speculative. under what circumstances would you discover that the gravitational wave is actually a graviton?
Yeah. I mean, I
Is
don't
it possible to measure this? Freeman Dyson wrote a paper about whether or not you could determine quantum effects with the gravitational waves. And what he discovered was that to get a measurement, you would have to have a measuring instrument, which would be a black hole itself. I mean, its mass would be such that it would collapse.
Okay. Well, this makes actually quite difficult to understand if the gravitons are there or not.
Yes.
Yes.
Well, I only asked the question because I wondered if you thought about it.
No, actually, I didn't think about this. I'm sorry. But this is a very interesting question.
Mike, you had a question? I'm just wondering if there's been any thoughts or any studies that have been performed to look at what are the actual realistic prospects of identifying this signal in the presence of noise and in the presence of glitches. For example, in the current LIGO detectors, there's a very high rate of glitches, and that impacts whether we think a signal is astrophysical or not. Do you have any comments on that?
Yeah, I mean, actually, it's a problem. We still have we never really start to think about this, but with some colleagues in Toulouse, there is this idea to actually understand how to proper extract this kind of signal from the data stream, because yes, it really looks like a glitch. I know it's kind of difficult.
Okay, thanks.
Thanks for the nice talk. I had a couple of questions. The first one was, it may be that I misunderstood what you had written down when you were writing down your quarter pole formula, but it looked to me like you were summing up over individual particles. Is that right?
Yeah.
So that doesn't sound to me like the right thing to do. So gravity, of course, general relativity is not a linear theory intrinsically. And consider, for example, the following configuration. Imagine I have a disk which consists of infinitely many tiny particles, all just in a loop going around, right? So, and it's a stationary configuration. If I do it particle by particle, each particle has a time varying mass quarter pole moment. So I would add them up and I would get a significant gravitational wave signal.
I think that for symmetry question, actually, the signal should be zero.
I'm sorry?
The signal is zero, I know. But
Yeah, the signal should be zero. Exactly.
But also in quantum, I think this problem should be actually not there. I mean,
Okay.
I don't understand how this problem can actually arise because they should cancel all the contributions. They should be zero. We can test it.
Okay. All right. So maybe I misunderstood the expressions that you were using. I'm glad to hear that there is no gravitational wave signal in that case in phantom, because in fact there shouldn't be. That's perfect. Okay. So thank you for the reassurance and apologies for misunderstanding. My second question was, you pointed out some potentially quite high frequencies, for example, in the case of a tidal disruption of a sun-like star, where you said that frequencies could go up to, although you said the nominal frequency is 10 to the minus 4 hertz, you sort of drew on a plot that it might go up to 10 to the minus 2 hertz. And that seems to me to be coming from the fact that when you showed your waveform as a function of time, you have a pretty sharp spike in there, right? And okay, anytime you have steep gradients in the time domain, that corresponds to high frequencies in the frequency domain. But it's perplexing to me because I don't quite understand why you would have this very sharp spike rather than a more gradual sort of petering out of the signal at lower frequencies. So is that a resolution issue? I mean, are the high frequency signals there because of some time domain resolution, which then when you do the Fourier transform ends up being a high frequency signal, or do you think that they're real? And if so, how do you actually get things orbiting close enough to give you those high frequencies of 10 to the minus 2 hertz in the case, for example, of a disruption of the sun?
I mean, actually, it's not 10 to minus 2 hertz. It's not the case of the sun. I was actually talking about the case of white dwarfs that are disrupted by mass level. In the case of main sequence stars, the higher frequency is around the median. We don't go to such a high frequency.
Okay.
Sorry, I was not clear probably.
Okay. No. Yeah. Sorry. No. I think you wrote down in fact 10 to the -4, but then on the plot, the green arrows in your plot looked like they might have been going up to 10 to the -2. Okay. No. Okay. That was my misunderstanding. But do you think there is in general, do you think there is there are any resolution issues in the time domain that might artificially give you higher frequency components to the signal, or is that something that you have good control over?
I think Daniel Price can answer this question.
I mean, we definitely did resolution study. There's no difference with resolution at all. So
Do you have another question from before?
well, in fact, the stellar structure doesn't come into it. Is that true, Martina?
It's also true that for now we just test the polytrope sphere.
For the first spike, though.
Yeah,
it
it's
doesn't-
true.
the stellar structure doesn't-
I think if you don't hold it, people on Zoom can hear you.
So as far as I understand, in the first, maybe you can bring up your plot with the stuff at the ripples and things. This last one you had, yeah. So for that first spike, that's mostly just orbital motion. It doesn't really matter what the star's made of, and it's only really in this later stuff that you actually see the star physics. Maybe Martina, you can expand on that.
No, yeah, actually, there are also some previous studies that actually shows that this is mainly, as Daniel was saying, this is mainly due to dynamics, not to the internal stellar structure. So yeah, actually, I confirm this. And in any case, it could be interesting also to try just to verify to maybe not just use a polytrope, but just try to simulate a more realistic star. In any case, just to do a double check. But it's something I didn't do so far.
Could you remind me about why that? Don't bother about it. Could you remind me about the setup for this? It's got E is equal to 0.8.
It's the eccentricity.
Beta is equal to 1. It's a binary.
No, sorry, here actually is an error. Beta is equal to 2. Sorry, not 1. It's an error. It's a star around a black hole. Actually, the black hole is expressed through the Kerr metric.
Martina again for this talk.